Hello.
Hello, how are you?
I'm good. You?
Not bad. Not bad. All right. We got people popping in. That's good. Even a couple minutes early, which is nice. Oh. How are things, Chase?
Uh, things are good.
That's
Sorry, I just had to find the unmute button.
no worries. I'm still figuring all this stuff out too. So there's a chance I could just kick everyone out of this meeting accidentally. It happens.
Yeah.
Yeah. How are your other online classes going? Things going okay?
Yeah, everything's going good.
That's cool. One thing I found is these cameras, like in this situation here with the laptop, they're good. When I take them into the shop, they're absolute potatoes. Um, they're just terrible quality. So I might figure out a way to shoot some different welds for you guys when we get to the welding section. I might shoot them, maybe not live. I might shoot them with something else and then upload them. And I might have you guys reference them that way. Yeah, it's kind of interesting. This whole online thing. Some people are good with tech, and then there's me. So I'm still trying to figure this out a little bit. But we're getting some people in here. That's good.
Hello.
Hello. What's going on?
Nothing much. How about you?
Just figuring out tech, trying to figure out how to shoot the best possible videos for you guys. These cameras don't work well in the shop. I don't know why. The color's all washed out. It just looks terrible. So I got to figure out a way to shoot some welds for you guys. So, because I wanted to show you guys a bit of an arc hunting or a stubbing type of situation today. I was trying to film it and it just did not turn out. So I might see if I can find a video or somehow film through a welding helmet with, say, my cell phone, and then link that video for you guys at a later day. So, yeah.
What about GoPros?
GoPros, I've got one. In fact, I've got one here, and they do work. But with the autofocus, they have a hard time shooting through a welding helmet. So the field of depth is okay, but when you're placing them up against a welding helmet, it has a hard time shooting through all the different layers of the helmet and still keeping focus on, say, the weld. So that one sounds tough. I'm going to play around with it a little more, though, see if I can't figure out something for you guys.
Oh, okay. I see.
Yeah, it's not working as good as I would like, but yeah, there is a way to figure it out. So we got 9 people in here. Wait for a few more, and then we're going to kick off the second half of that slideshow from yesterday. So we'll get that going for you. Yeah. Hi, Nadine. Getting people in, which is good. That was wait for a couple more, and then start a screen share, and then we'll start things happening here. What are we learning today? Second half of the PowerPoint from yesterday. So we left off about halfway yesterday. Gonna fly through the last half of it and get you guys the quiz that goes along with it. And that'll be that. Want to do some shooting of some welds for you guys, but I'm having trouble with camera quality. So I got to figure that out, and then we will get some stuff filmed up for you guys. So I've done it a certain way before, but it's a super long process. So,
Buddy, put on headphones.
yeah, I've shot it with a DSLR in video mode.
My headphones are dead, man.
And then I've used...
Actually, I'm starting to just switch positions.
Yeah, and then I've shot it through a big welding lens, and that has worked in the past, but it's a real pain in the butt process to do. So, yeah. Yeah, we'll give a couple more minutes, and See who else decides to join us for today. How many views you got on TikTok now, Sagar? I know we were talking in class about that video had like 1 million+ views or something.
I don't know. Let me check really quick. I haven't checked in a little bit. Jeez, it popped up to 1.6 million.
Man, TikTok famous.
It's such a useless title to have, but it's kind of cool, I guess.
Yeah? What I'm gonna search this up later. What is it? Or is it not appropriate for me to be viewing?
I don't know. You can do it. I'm just making some car noises.
Car noises?
Yep.
Really? And it's got 1.6 million views.
Yes.
Wow.
Your
People-
videos is low-key been on my For You page before.
Really?
Yeah.
Dang. Yeah, I posted one video that got like a couple thousand likes,
Mhm.
and then I'm like, okay, that was pretty interesting. I'll post another one the next day. The next day I posted that one, absolutely blew up. That's the 1.6 million views one.
And is it the same as your handle on here? Snowman Sagar?
No, my username for TikTok is Canadian_snowman, but with a 0 instead of an O.
Oh, okay.
So yeah, it's pretty cool. It's like, hey, I'm TikTok famous. It's like, oh, that's cool.
Yeah.
But like, it's such a useless title.
Well, you need those brand deals, right?
Yes, sir.
Yeah, we need some sponsor posts, some brand deals.
Yep.
Yeah, that's funny. So that's cool. 11. Hopefully we get a couple more because we're missing like 9 people. Gonna give them 2 minutes. If they don't get here, we're just gonna start without them. So yeah, it'll be interesting. Yeah, I think my wife's got a TikTok thing, and they're like one of her videos got like 50,000, but that's about it. So
Oh, it's
yeah,
not bad.
no, it was just we were driving back from BC, and there was a construction worker holding a sign. He was dancing and having a good old time, and it was like pretty cute. So we threw that to some sort of music, and I don't know, it's got like 50,000 likes or something like that. I don't know.
Huh. Not
I'm
bad.
not. It's not my thing. I don't even have TikTok on my phone. So
Yeah, it's just good entertainment, I guess. It's pretty addicting.
oh yeah, it could easily be. That could be a lot of fun, right? I mean, it's all the social media stuff's good and wholesome until, it's not. It's all good for a little while, and then it starts getting crazy.
Mhm.
All right, so since I have nobody else, let's get this going, and we're gonna throw up this screen here. We're gonna share this one, and then we are going to go to present mode because that's nicer. Gonna hide some faces. And yeah. Ooh, is this not where I want to be? Gosh, where did that? Oh, okay, so we've done this. Sorry if I'm giving you guys seizures here with my rapid screen flicking. So we were here. This is where we're at. So we're going to talk about stubbing versus arc hunting. What is stubbing? What is arc hunting is the big question. So stubbing is when you have the welder set up, because all these controls on the welder are manual. You set them all. It does not auto set. So you control the wire speed, how fast it comes out the end of the gun. You control the voltage, which is how much force basically gets pushed through the weld. It helps shape puddle fluidity and the overall shape of the weld. And then we have the wire speed also influences the voltage, so, or the amperage. So wire speed and amperage are directly correlated. But basically, if you just have something like 16.5 volts for your welder, for gas metal arc welding, and then you decide to crank that wire speed to 450, you're not going to have enough power to burn off the wire coming out that fast. So that wire is going to bash off of your steel plate, and just, it's going to, bash off your steel plate a whole bunch of times. It's going to be a waste of wire. It'll kind of pop and spatter, and there'll be chunks of red hot wire 2-3 inches long flying everywhere. It's just mayhem and chaos, and not anything like welding. Arc hunting is the exact opposite. So you got a whole lot of voltage and amperage, but not a lot of wire speed. So your wire is going to travel slowly from the end of the gun. It's going to touch the plate. It'll burn off, and then it'll retract almost all the way back to, well, it won't retract, but it'll burn off almost all the way back to the contact tip, and then slowly travel down and burn all the way back again. And it's, I mean, of the two, I would rather a bit of arc hunting than stubbing, because stubbing is unmelted wire entering your weld area, whereas arc hunting is you're not forcing enough wire into the weld area, but you're still melting all the base metal. So if we had to pick one as being better than the other, arc hunting would be better, but neither are what you want for welding. What you want is that nice balance where you get the wire burning off at a nice, decent, acceptable rate. It's not hitting too hard. It's not bouncing off your plate. And you're not getting that burn back all the way back to the contact tip either. So that's kind of what we want as far as this stubbing versus arc hunting. And I'm gonna try and shoot a video for you guys and show you what that is. I'm gonna try and do that for the next class or at some point here soon. Arc hunting is what happens, well, when the wire goes too slow. We just talked about that one. Maybe from too slow of a wire feed. It could also be like a dirty liner in the gas metal arc welding gun. That liner, if it's got junk in it, it's going to bind up on that wire, and it's going to have a hard time to come out the end of the gun the way we want. Loose wire drive rolls. So we talked about the drive rolls yesterday. I don't know, we're going to talk about them today actually. So wire drive rolls are what push the wire from, or pull the wire from the roll and then push it out the end of the gun. So if those aren't set to the right tension, those could be just spinning their tires and not driving any track or wire anywhere. So they'll just be slipping and the wire won't be moving. Or a compromised contact tip. Say you had a whole bunch of arc hunting, and at one point it burnt all the way back to your tip and melted the wire to the end of your tip, or just partially covered it. That's gonna make it difficult for that wire to come out the end of the gun for you. And that could be one of the causes of arc hunting, but normally it's just an imbalance of voltage versus wire feed speed. Stubbing is either from too fast of a wire feed speed or too low of a voltage setting. So you can correct either of those. Since they're basically the same problem but different, you can correct them both with either adjusting the wire or adjusting the voltage. Kind of a neat way of doing it. It all depends on what you're looking for. If you got working on big, thick steel, you can run pretty much as much wire as you want as long as you got the voltage. If you're working on thin stuff though, we have to work with lower wire feed speed, smaller voltage, so we don't burn through. So yeah, power sources for gas metal arc welding. We're not gonna get too crazy into that. Kind of the more 11 level to 20 level. I like to get into power sources more in depth, but we're just going to touch on this for a little bit today here. So welding power sources are constructed to meet specs set by NEMA. It's the National Electrical Manufacturers Association. Duty cycles can range from 20% to 100%. And there should be noted when setting up to weld. So most welding machines are 60%. But if you're working in a big industrial shop and you guys are working on a lot of large steel, so big beams, you're doing flux core, maybe metal core, those machines are going to be rated heavier. They're going to be designed to take more abuse and weld longer. The way we rate duty cycles is how long that machine can be set at 100% for and weld in a 10-minute period. So a 20% duty cycle machine, you could crank it to full maximum, hold that trigger straight down and just let this thing weld. It will weld for 2 minutes before it overheats and shuts down out of 10. So then you got to wait the rest of the 8 minutes. Then it'll reset. Then you can weld again. We don't generally force machines into that high of a zone though. It's just not good for the components. So we like to run them in the middle of their capacity. It's kind of going off Sauger's car talk here and car noises. Just because you can force 40 pounds of boost through a motor and it can take it, doesn't mean you should all the time. So why not run something a little safer like 20 pounds of boost and run it all the time? And instead of 40 pounds of boost for a couple Hail Mary passes and hoping your motor doesn't blow up, right? So that's kind of duty cycle. And just because you can, you shouldn't. And if we're talking cars again, you hear a lot of people talk about injectors and duty cycle of their injectors. So if they got a big motor with high demand, they want to know that they've got enough injector to keep the motor fueled. Because if you underfuel the motor, you cavitate it, you blow it up, it's not a good thing. So a lot of people are going to see what their duty cycle of their injectors are and how much the injectors have to work to provide the fuel for certain runs. So a little off topic, but trying to link it back to some relevant stuff that you guys might enjoy. A lot of our welding machines are 60% duty cycle. That means you can run it full out, 6 to 10 minutes. It won't do 10 to 10. That's not going to happen. We can get machines that will do 100% duty cycle, but you are paying an exorbitant amount of money for that because everything is way overbuilt, designed to take a lot of heat, a lot of constant stress. And it's just generally not practical. I've never really had too many issues with duty cycling machines. A lot of the work I've done has been gas metal arc welding and shielded metal arc welding. Nice thing about shielded metal arc welding is you've got a welding rod that's about 12 inches long. You burn that down to 1 inch long, you stop, you change the rod, you start it up again. So you're always taking those little breaks. When it comes to gas metal arc welding, it's going to be tough to hold that gun up and to hold that trigger down for 10 minutes straight. So often you're going to need a break. It's not very often we're ever going to find a weld that's that big where we have to run the welder for 10 minutes straight. So we take enough breaks to let the machines cool down. So we never really end up going over the duty cycle for a lot of these machines. Can it happen? Yes. Does it happen often? No. So gas metal arc welding applications require a constant voltage power source. Yeah, so that's pretty straightforward. Gonna go over that. We're gonna basically go over this. We don't need to know too much about that. This one here, constant voltage, also known as constant potential, is what we use for most gas metal arc welding applications. And also most gas metal arc welding applications are going to be set up so you are running direct current electrode positive. DC RP is known as reverse polarity. But if we're talking a little simpler terms, direct current electrode positive DC EP is what we run in most machines. There are some DC EN electrode negative applications, but we don't see it very often. Yeah. Wire feed controls and drivers. This is more our speed here. We got that spindle, roll of wire on the back, which is cool. Those wires come in different sizes, so that's something we need to be aware of. Wires can range down from like an 0.17 to an eighth of an inch. Like there are some big wires out there. 1/16 is pretty darn big. I have seen them bigger, but we're running an 0.35, so 0.035 thousandths of an inch. For flex core, we're gonna run an 0.45, so 45 thousandths of an inch. It's just kind of standard. It's good to learn on. You're gonna run across that everywhere as far as sizes go, and it's just easy for us to learn on. Good starter wire. We got the variable speed electric motor. That is what drives our wire at the different speeds we want, right? We got control mechanisms. So we are going to be able to fine tune wire speed, voltage, amperage, arc force, some stuff like that. Drive roll assemblies and accessories. Obviously, if we got the drive roll unit, we need the rollers in there to push the wire, and we have to have the correct sized rollers for the wire. So if you got an 0.35 wire, you got to run an 0.35 roller to match it. This picture here it just makes me cringe every time I see it. Because what this person's doing is they're going to cut the wire. What do you think is going to happen to the wire there once it's cut?
It's going to unspool.
Exactly. And there is about 1 million wraps on that roll. It's 44 pounds when they're new. So it's a lot of steel. A long length of wire. I have no idea how long it is, but I would guess it's in the kilometers. And they're not cheap either. So if we just let that flap around and unspool, that's a waste of a lot of wire. Yeah, that could easily be avoided just by holding that end. So hold that end, and then what I do is after we cut it, I'll take the end and I'll feed it through a hole like that, or this one, and I'll bend it over. That stops it from unspooling, keeps it nice and neat. Then we store that wire till we're using it next time, and life is good. What we have here is a drive roller setup. So on the top, right here, we have a tension roller. There is no motor driving this. This has just got bearings in it. It's simply held on to this little pin here with a retainer clip. But this goes on the top of your wire, and it forces your wire down into this roller here. Now this one has the electric motor attached to it. This is the one that's going to have variable speeds, and it's going to have a U-groove setup here. So U-groove setups is simply a groove shaped like a U to sit the wire in. That way it's got a lot of surface area, a lot of contact. If it's just a flat roller, we've got a very little small contact patch. And we want more. Kind of going back to cars, people air down their tires so they get more contact, more surface area with the track surface, or when off-roading. Same kind of situation here. We want that surface area to grip and push that wire along with. If we just had a flat roller, we'd have very little surface area, and we would not be able to drive that wire forward as well. And basically what happens here is we got a roll somewhere back here. It comes off, goes through here, it gets driven through the liner. That liner there goes all the way through the gun, basically stops at the contact tip at the end of the gun, and then out the end of the gun to your weld. So pretty simple all in all. Just this picture doesn't show it very well, and sometimes it's hard for you guys to understand where this is located, but this is located just inside the cover of the welder.
I have a question.
Yes, go ahead, ask it.
If we increase the roller size, would we see a difference in the wire speed?
No, because these are designed to take a certain size roller size, and that's it. Because if we increase the roller size, we increase the roller size by 1/2 inch. From the center point here where my cursor is, that's gonna be the center point of the spindle to the surface of this. We're gonna gain a 1/4 inch, right? So then what would happen is the wire would have to come through here, climb up over that 1/4 inch, then back down. So it'd rub here and it would rub
Bit
here.
resistance.
Yeah, it would create more resistance. Plus this probably wouldn't have enough adjustment in the take up to allow it to come up that extra 1/4 inch to, what do you call it? To drive it faster. And also when you put a bigger tire on, you do the exact opposite. You don't drive things faster, you drive things slower, right?
Yeah.
Because this is still spinning here at a certain speed, but the outside takes longer to come on a full rotation. So that's why people put smaller pulleys on superchargers to get higher compression. Yeah, because smaller, you can spin smaller things faster because you got less rotating weight. But yeah, it would not give you any advantage if you're doing this. So we're gonna move on to the next slide. What we have here is the end of your welding gun. And this is a nice new clean one. Ours aren't looking quite this nice, but all of these are going to kind of show you what we have here. So obviously this, well, maybe not obviously, this yellow thing here is a trigger. We have the handle of the gun. We got the curved neck here. A lot of the guns will have this little hook on them just for hanging them up on something, which is kind of nice. And then what we have here is we've got insulating material. We have our gas diffuser right here. It's got the holes in it. So we're releasing gas from our gas bottle through a line all the way out to here. This gas gets dispersed through these holes. This cup here is actually going to be over top of this. And then the gas exits around this contact tip out the end of the cup and shields your weld from atmospheric contamination. This contact tip here is going to go right in the end. It's sized to your wire, so you have to have an 035 contact tip if you have an 035 wire size. If you stepped up to 045, it's got to be the same thing. Contact tip's job, transfer energy to the wire to help you make the weld. So these can get worn out. You can lose contact through there, and basically you don't get a nice weld. It will kind of pop and stop welding in the middle of a weld and start and stop, start and stop. Kind of like stubbing, but not as extreme, and it's due to losing contact with a bad contact tip. Drive roll assemblies. So we're gonna go back to drive rolls for just a second here. They can come in a bunch of different configurations. So we can have a 2 roll setup, kind of like the first picture I showed you. I think it's like this one here. It's a 2 roll setup. So we got one on the bottom, one on the top. But really we only have one drive roller because only one motor or roller has the electric motor hooked up to it. 4 rolls, so it could be a dual setup. You can have 2 electric motors, 2 drive rolls, 2 idler rolls on top. This helps you go a farther distance. 2-wheel drive versus 4-wheel drive, right? Let's think of it that way. 2-wheel drives, yeah, they work. But 4-wheel drive gets you farther places and generally a little more dependable. And it's not so hard on the one set of motors, because if you're trying to push that wire and you got a dirty line or a compromised contact tip, a lot of resistance on it, that little electric motor is working super hard. But if we got 2 electric motors working in tandem, so more like an all-wheel drive system where they work together, it is going to just be easier on everything overall, and it's gonna work better. So it talks here, right here, about being push or pull or push and pull. So when we talk about push and pull, basically what it means is we're pushing the wire out the end of the gun with the drive rollers. When we pull, we actually pull the wire off the roller and basically pull the wire out the end of the gun. I've got some pictures in the slideshow. It's going to make it a little easier to understand. This here is just saying 1 roller or 2 is usually the top is the idler, and they'll have a tensioner. It does not do any driving. It just is the tension roller. It keeps that wire down in the groove, and it helps keep it there. Without that tension, that's going to spin. You won't have that wire pushing forward like you want, and it won't be a good setup. So we can see it right here. We've got our 035. You notice the numbering on it, which is kind of nice. We got this one's just going to be a flat one. It won't have a matching U-groove, so we don't have to change the top one whenever we change these. So if we change our wire size, we got to unscrew this, put a different one on for 045. And we got to match our contact tip to 045. Contact tip's going to be on the end of the gun. We don't have to change liners. Liners have the ability to take different size wires up to an extent, obviously. We got our pressure roll. So this, as you tighten that up, puts more pressure on this, which pushes it down to here, which creates a tension between there. So, and that's what gives it the traction. The pressure pushing it down gives it the traction, comes out the end of the gun. So what we have here is a dual drive roll setup. So this is the all-wheel drive system. Instead of just having your back wheels do all the work, we have some front wheels too. So we are going to have a roll of wire back here somewhere. It's going to come through here. This is going to be down, clamped on the wire. So we got a gear drive here that meshes with the gear on the electric motor, the electric drive motor. Same with this one. And they're going to be wired in series. So you're going to pull the trigger. They're both going to turn on at the same time. These are going to pop down, tensioners go up, and that's how that works. So these ones are doing the driving. These ones are just along for the ride. So different shapes of drive rolls. When we first started doing this, we had to play around with the designs a little bit. We're talking about Alexander back in 1924. You know, he had to mess around a few times, find some drive rolls that work, some shapes to give it that push on the wire. So we've come up with a few different things. We got a V-groove. V-groove is the most common. A U-groove, knurled, or a combination of the above. So U-groove, pretty common for the solid wire stuff. Knurled V-groove is a combination of the two, and that's what we're going to use for flux core arc welding. So flux core is a softer wire, and the knurling gives it a little bit more grip, kind of like a mud tire versus a slick, and it's going to propel that wire forward. It's going to bite into it a little bit, push it forward. Also, size of wire the roller is designed for is going to be stamped on the roller. Not always, but most of the time. It's going to be stamped pretty clearly, and you'll be able to see it. Some rollers are the same size on both grooves, because rollers usually have two grooves, so if you wear one side out, you can flip it. But some are 035 on one side and 045 on the other. So we need to be aware of that if you guys are ever working on those parts of the machine and disassembling it. Just got to make sure the wire size that we are or the roller size matches the wire size, and that if we flip it, we still have the correct roller size. Otherwise, we're not going to do any welding. Drive rollers need to be a minimum of 3/4 of an inch in diameter to keep the wire from curving as it's fed. So if it's too small, it puts what's called cast in the wire, and cast is a bit of a curve. Basically 3/4 of an inch and bigger are what we use to push a wire along. It just stops putting pressure in a small area of the wire and curving it. Curving wire is going to create resistance on the inside of the liner. It's going to just be tough to feed out the end of the gun and out the end of the contact tip. And if it's got that cast or curve in it, it's going to wear on the outside of the contact tip as it exits the welding gun, and it'll wear a groove into that contact tip and cause it premature wear, and then we'll have to replace it. So there are some definite bad things that can happen if you're trying to run small drive rollers. All right, so what we have here are the shapes and sizes. I talked about Alexander in 24, patented that system. I don't know if he designed any of these, but I'm sure he designed something similar to him, because he had to drive that wire somehow. So this is knurled. This has got some cross hatching on it, and that just kind of grips the wire, pushes it forward. This is a flat, this is a slick, and basically that just provides the tension, pushes that down here, that grips it, drives it along. It's an okay system, but here we don't get the surface area contact we well, if we need more surface area here to drive it better. So we came up with, you know, a couple different systems. We got an angled roll system. So we got an idler, then we got a drive, or sometimes it's an idler, and then the drive is going to be a third one off to the side pushing against these two. I've never run into a system like this. I've used a bunch of welders. I've never run into a system like this. I don't think we actually employ systems like this anymore. I think technology has kind of moved on from that. Right here, what we have is the V-groove roll system. I think they're one of the best. But what I like the most is a V-groove with the cross-hatching on the insides here. So it's a knurled combination of the knurled and the V-groove. That gives you good surface area. You got lots of contact here and here. You got this applying the pressure. It's, you know, got double the contact area of, say, it's just a knurled system. And for the solid wire, we have the U-groove system. It's great. This shows a bit of a gap here, but normally this wire seats in, sorry guys. Normally the wire seats in a little better, and you got full contact across here, so lots of surface area, and that will work out well. Those are pretty common across all solid wire setups. So like I said, if you find an old machine, you may find something like this angled roll system, but I haven't seen any in my time, and I've been doing this since I was 18, and I'm getting old now, so it's been a few years. Talked about the size being stamped on the rollers. So here's a great example of it. So this is an 035 V groove, or it'll have a U on it, whatever it might say. Sometimes we flip these over and it'll have an 045 stamped on the other side. I know some of the ones I have in the shop are like that. Wire feed control panel. So this is what's on the front of the welder. This is where we start to get our ingredients right for a recipe. And basically, we need a recipe, a good recipe to get a good weld. And that's, you know, a recipe could be with your voltage and your wire feed speed. I mean, a pretty basic recipe, but it's just an easy way of thinking about it. Same way with the gases. They've got different recipes for gases. And sometimes it's 3, 4, 5 ingredients. And yeah, that's just an easy way to think about it. And I like to make references to other CTS programs as well. And Ms. Levine just walked by in the background a few minutes ago. So that got me thinking about pastry arts and culinary and stuff like that. Yeah, but basically on the wire feed speed or the control panel, we got voltage and wire feed speed. So it'll have a place to plug in the trigger control. It's going to be a multi-pin connector with a twist-on collar. Pretty simple. We don't really play with that too much. But I do, when I change over parts on guns or I take a gun apart, I have to disconnect that. So yeah. Power source. And basically what it says below that is power corrupts, absolute power corrupts absolutely, but it rocks absolutely too. Kind of a play on an old saying. But yeah, it's neat. So voltage, let's talk about that for a minute. And we got amperage and polarity, electrode extension, stick out, slope. We've kind of learned a bit about all of these. Inductance, haven't really talked about that. Not really something we need to worry about too much, or the slope. It's just not something that's going to affect you guys at the grade 10 level. But these all have an effect on something. And does anybody maybe have an idea what it might affect? No.
Weld quality.
There you go. The quality of our welds. Awesome. Nice. So voltage is the force that overcomes resistance to allow amperage flow. It controls puddle fluidity. I spoke about that earlier. It's going to help shape our puddles. So if we got low voltage, our weld is going to be kind of tall, narrow, and pretty humpy. It's going to be like a killer speed bump. You guys ever drive along and just see a speed bump that you're like, oh gosh, I better slow down for that one, because it's just enormous in comparison, or it's like really tall or really abrupt. And basically, your weld's going to look like that. It's going to be narrow and high, and it's going to have a hard transition from the base metal into the weld. Just isn't going to look good. And then you crank up the voltage a bit, and that's going to basically turn it into a normal style speed bump. You know, it's got, you know, a little crest in the middle, but it's got, you know, a fairly gradual slope from the base metal to the edge of the weld, and it's going to have a better shape. It's going to be wider but lower. So, and if you really crank that voltage, it's going to flatten that weld right out, and it's going to be super wide and super flat. Not always a good thing, because big weld puddles are hard to control, especially when doing things like welding vertically or overhead. You don't want a whole lot of puddle fluidity. You want a very controllable puddle. Voltage also controls arc striking. So the more voltage you got, the easier it's going to be to start your welder. Higher voltage settings result in wider, flatter beads with shallower penetration. We kind of talked about that. Amperage, I'm going to move on to that. Is amount of current flow. Controls your penetration. So how deep that weld sinks into your base metal, how much mixing of the parent metal and base metal you have. Controls your burn off rate. So if you have a high amperage, you're going to have a high burn off rate, which means you need to have the wire feed speed to back that up. A wire feeder's amperage is directly influenced by wire feed speed. So there you go. Higher amperage settings produce a narrower, higher bead with less metal fluidity and deeper penetration. There may be a time, 20 level, where we demonstrate this. What we'll do is we'll weld different welds using different settings, and we'll stamp all those settings into the weld so we know exactly what it is. And then we're gonna cut them, polish them to basically a mirror finish, and we're gonna etch them with pretty strong acid that Miss Bailey gave me. And what it does is it shows the weld metal versus the base metal. They're gonna look different. They're gonna appear different under the acid etching. And it will show you your penetration into the plate. So we can measure out roughly where our original base metal was. And we can draw those lines on, and we can see how far past those lines our weld goes in, and it mixes up with that the base metal and the parent metal. So it's a good way of showing penetration in a weld, and it's cool. It's just fun to play with too. I kind of feel like Walter White when I'm doing it, because you got to dress up in face shield and big gloves and all that stuff, and it's fun. Polarity. Polarity only applies to direct current, not AC. So AC is alternating current, which switches direction 120 times a second or 60 times a second. 60 cycles a second, 120 direction switches is what it is. When doing that, we got all these numbers here: DC, EP, EN, DC, RP, DC, SP. So EP and RP are the same thing. EN and SP are the same thing. And what it stands for, DC is always direct current. The EP is going to be electrode positive. The EN is going to be electrode negative. RP is reverse polarity, and SP is straight polarity. So now you're confused. 2/3 of the arc energy is always on the negative side. So when you weld electrode negative, you get a higher burn off rate with your wire. You need to provide more of the wire, and this doesn't work quite as well as electrode positive or reverse polarity. Polarity will affect your deposition rate, arc characteristics, and penetration. So earlier I talked about a pretty simple recipe with amperage and voltage. When we start putting polarity in there, we start changing inductance. Those are other ingredients that can all change the outcome of your welds. So we're kind of thinking of it as a recipe, a basic recipe versus a more complicated recipe. We're going to keep this one basic though. AC current is not used with gas metal arc welding. AC is alternating, and what you will find is AC sounds different. It requires different machinery to handle alternating current. It's kind of a noisy system, AC is often used for aluminum TIG. And you got high frequency AC aluminum TIG. And they call them buzz boxes. It just makes a bunch of noise. It's weird, but that's just how these machines sound. The distance between the end or electrode extension and stick out. This is an important factor that everybody has trouble with. So basically, electrode extension or stick out is how far past the end of your contact tip the wire sticks out before it makes contact with your weld. This wire, even though it's steel, is a terrible conductor of electricity. Now that sounds crazy because it's all, you think, oh, steel, it's a conductor of electricity. Yes, it is. But in the conductor world, it sucks. It's not number one, not at all. There are many things above steel that conduct electricity better. Does anybody have an idea what the best conductor, besides superconductors, of electricity would be? It's found on the periodic table of elements.
Is it iron?
No. Iron's actually fairly low as far as conductors. It's okay, but it's not great.
Copper.
Copper's up
What
there.
about
It's above iron.
Gold.
Gold is the answer.
Oh, I was gonna
Gold.
say salt water.
Oh, yeah, saltwater would conduct, but we need a solid to conduct that electricity, right? So gold followed by silver are some of the best conductors. That's why if you ever go on YouTube, you can type in gold recycling from electronics. You got guys picking up all these old electronics, smashing out the boards of them, melting them down, and recycling gold out of them. It's going to take a lot of cell phones to get a chunk of gold, but it's in there. Your phone's got gold in it. Your laptop's got gold in it. Stereos, all that stuff, because gold is a great conductor. So they use it quite sparingly, though, so it is going to take a lot of recycling to get any amount of gold that is going to be worthwhile. But yeah, gold. What's the symbol for gold on the periodic table of elements?
I think it's AU.
That is correct. Yeah, and silver is what? AG?
AG.
Yeah, there we go. All right. That's not bad for a welder. I didn't like science, but I learned, I find some of the stuff interesting, so I paid attention to some things. And yeah, those conductors are awesome. Unfortunately, we don't have, I mean, it's just not practical to make contact tips out of gold. It would be super cool, and if I wanted to really flex out, that would be kind of a neat accessory. But gold also has a fairly low melting point, so it's got a lower melting point than copper. Copper can be alloyed, and so it can take that heat. Gold can't. So yeah, mild steel is not the best conductor of electricity. We talked about that. Surprising. Aluminum conducts better than mild steel, I believe, even. So old houses used to have aluminum wiring in them. Then we moved to copper, because copper is a better conductor. We got the ability to produce it better and more consistently. So yeah, that's kind of neat. There's some old history lessons for you. Increasing electrode stick out decreases amperage. So the more stick out you have, the more resistance you have in that steel. So for every little bit of distance you have out past that contact tip, you are losing amperage because of the resistance. So that's when you need that voltage to push it to get that weld. But when we were welding, some of us were far away from the plate and we were getting that pop, 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 pop kind of thing, and little chunks of red hot wire were breaking off. That is because we don't have enough amperage to fully burn off the weld or the wire when we're welding. But when I was working with some of you, I grabbed the end of your welder and I kind of jammed it in there nice and close to the weld. That reduces the amount of resistance we have through the distance on the electrode wire. And then we can transfer that to the plate. So we get a much better weld with shorter stick out distance. So there we go. Decreasing stick out increases amperage.
Oh, honestly, it does.
All right, so short stick out increases penetration, which is good because we're not losing, well, we don't have that resistance, we're not losing the amperage. Yeah, keeping things close and tight is going to be the way to do it, especially with gas metal arc welding. Flux core is a little different, but we don't get to that till 20 level. So I kind of talked about the wire drive systems earlier. We got the pull, the push-pull, and just the push systems. We're going to go over those quick because it's already after 3 and we're going to wrap this day up here. So push system, push type is pulled off the roller or out of a drum and then pushed through a conduit liner up to 15 feet to the gun. So that's the type of systems that we are running in our shop, is a push type. So we're gonna basically push it from the back all the way out through the welder, through the gun or the hose or cable, and out the end of the gun. Most common, yes it is. Yes, we have these in the shops. And it's gonna be like this. So in this system, this gentleman might have a small roll of wire up here, but also in some of these systems, they feed wire through this liner and they have it in a drum back here that could be 1,000 pounds. I toured a shop in Montreal. They did all the steel for the One World Trade Centers. They were running systems similar to this, and their wire roll was actually a 55-gallon drum full of 1,000 pounds of wire. And that way they're not wasting time changing small rolls because they're welding so much and using such big wire. And when you buy in bulk like that, you save on packaging. So a lot of what you pay for when you're buying wire is the packaging and the handling. So the more you buy in bulk, you get better deals. And those 55-gallon drums are a really good way to do it if you have a welder to run it. Whoever's got their mic on, would you mind muting that? It's just a little distracting for myself and everyone else, please. Thank you, I appreciate it. The pull type's usually associated with softer wires like aluminum. So we can do MIG welding aluminum. They have a different gun. They're a little different shaped, and they're gonna just use a small 1-pound roll of aluminum wire. And those rolls of wire are actually gonna be mounted on the gun. They look a little bit different. We got a picture of one right here. This is kind of the one I'm familiar with using. It kind of looks like Han Solo's blaster from the original Star Wars, except for the roll on it, because the whole front section really reminded me of that. But what happens is right here, that's where a roll of wire goes. It's a 1-pound aluminum spool. It's only about 4 inches in diameter. You put it on, it rotates this way. We'll feed the wire through here. Right below this cover, we can flip that up, and there are going to be 2 sets of rollers in there. Small little 1/2-inch diameter rollers. When we talked earlier about the diameter sizes of rollers, that kind of goes out the window when we're talking about aluminum. Soft wires, we can put that curl and kink in them because we're only pushing them a little ways, and the wire's soft enough, it's actually going to straighten out somewhat in this barrel of the gun right here. So yeah, in here you got 2 little roller setups. These things, when they're running good, they're great. When they're not set up well, they're an absolute pain in the butt because this aluminum wire is so soft, it bird's nests inside of here, so it all jams up in a ball. Then you got to pick it out, clean out all the wire from the gun, refeed it through here, back out there, and continue welding. But these have a speed control, so you control the wire feed speed on these guns, and it's usually on the bottom of the handle down here. There's a little dial you turn. We provide our gas and our power through this here, kind of like our welding gun, but slightly different. So they're pretty unique. Here's another version of it. This one, the roll is mounted upside down in comparison to the last one, so it hangs a little lower. You got your speed knob right here for your wire feed speed, and it comes out the end of the gun there. With those, what I normally like to do is I throw the cable over my shoulder, because the gun is a little heavier, it can't be hard on the wrist, so throwing the cable over your shoulder, the shoulder takes a weight, allowing less weight on your wrist, and you can actually weld longer and hold and maintain your angles a little better while doing it. So that's a nice little kind of pro tip if you ever get into welding aluminum. Push-pull type here has a set of rollers in the gun as well as a set at the trigger. So it's for going long distances, and they're kind of unique setups. I've never used these, but I know people who have. You can feed the wire of distances up to 50 feet. And there are situations where this can be really useful. So some people, let's say Irving Shipbuilding in Nova Scotia. I've met the owner of the company, and what they do is they build military vessels for the Canadian military. And they build them in sections, they assemble them all. But they keep all their welders outside on the decks, and they run these super long guns up inside of the boats, because it doesn't make sense to try and haul a welder around inside of a boat when you've got baffles and dual hulls and all these crazy, I don't even know what goes into those boats, but I've seen pictures of it. So these guys, they'll set their welders and they'll drag this cable 50 feet up inside, and they can just work all around on the inside of there without having to drag the welder around. So a little easier for them. Guns are different style, different shape, take a little bit of getting used to, but they're pretty neat. They're gonna look like this. So it's a combination of the last gun and a regular MIG gun. So we got a set of rollers up here. We got a wire feed speed here, trigger. It's got a curved neck to promote the contact. So these curved necks on these guns, the reason it's curved is so that wire gets forced to the outside and it rubs on the contact tip right on the inside here, which helps promote contact. So you always have that electrical contact for the tip. That way you're not getting choppy welds or anything like that. Whoops. See if I can back that up. These pictures didn't turn out very well at all, but these are more of a traditional style welding gun one. They do have a little set of rollers right in here that pulls the wire. But when you got the wires at the back pushing and you got these ones pulling, you can get up to 50 feet of distance versus the 10 to 15 that we have in our shops. So far greater reach, but also far greater associated cost. Yeah. So push style. This here says welding guns for gas metal arc welding will be air cooled or liquid cooled. We run liquid cooled guns when we're running things like flux core and metal core. Different gun, much more expensive, but flux core and metal core are very hot processes running high amperage and voltage. So we're not running superconductors in there, so we'll always have resistance in the system. Resistance, when it comes to electricity, is heat. Heat is not a good thing, so we cool those guns down so we don't burn them up. They've got a water pump, a radiator system, a cooling fan, and it pumps cooled water through the gun all the way from back to front, and then it recirculates it, cools it, sends it back through, kind of like the system on an automotive vehicle with a radiator and a pump. But yeah, instead of in an engine, it's in a welding gun. So curved neck, I explained that just a moment ago. That's to promote electrical contact for the contact tip. The guns, like I said yesterday, rated by their current carrying capacity. You don't want to run a little welding gun at huge voltage and wire feed speed. You're going to burn it up real quick. So that's when you go to the bigger one and you run it in that kind of middle comfortable zone. Right here, we have a little picture of the end of a welding gun. So this didn't turn out near as well as I was hoping, but basically one is the neck of the gun. It's right here. It's intentionally bent to allow contact between the wire and the contact tip. Cool, we talked about that one. So we're gonna go to number two. Number two is the next one. Insulation for the nozzle. We have to insulate this nozzle electrically. We're passing electricity through here and here. This energizes a wire out here, but we don't want this contact tip to be energized, because if you're pulling the welding trigger and you're welding and you touch this against something, that would arc out between that and the steel you're welding. That's going to burn a chunk of this off, deposit it in the piece of steel that you're working with, and that could be an instant failure depending on some job sites. And also, it's not good to have electrically conductive things exposed to you. So that's why we keep the electrical current contained within the contact tip here. So 3, gas diffuser. It's got them holes, gas comes out, circulates around here, out the end of the gun. This normally would be complete. This is just a cutaway so you can see everything inside. But yeah, that's where the gas comes out of. And it comes out the end of the gun here, over your weld, creating a nice happy environment for that. Contact tip, number 4. right here, made of copper that transfers electricity to the wire, must be sized to the wire. You see there's no gaps in here. It's got to be a tight fit the whole way through. That's what we're looking for. Number 5 is the nozzle face. So that's the opening right here on the end. Nozzle to contact tip distance can be varied depending on transfer type and voltage setting. I like to just set them almost flush with the contact tip slightly recessed. It just saves the contact tip from getting banged up or welded on. The guns have a liner. Oh, we are getting on the time here. Guns have a liner. That's what the wire travels through inside the gun. So from the back of the gun, where it's basically connected to the drive motors, a liner starts there, and it's usually helical steel, spring steel. They basically spin it in a circle. That allows it to flex without breaking. This is harder than the wire we're pushing through it, so it does not wear that much. It does wear eventually, and they do need to be replaced at some point, but not very often. And that stops the wire from rubbing on the electrical wires inside of the welding gun. It stops it from eating up the insulation material. If it's water cooled, it stops it from wearing holes in the water jackets and things like that. So yeah, that's kind of that for today. So definitely kept you for a few more minutes than I wanted. Sorry about that. I'm going to stop sharing this, and I'm going to go see who I have for participants. Has everyone dropped their name in the chat? Has everyone done that? If not, not a big deal. I'm just looking at names here to see if I have anyone else. So I got Riley, I didn't have earlier. Thank you for joining, Riley. Josh, I didn't have earlier. Thanks for joining, Josh. Christian, Jason, Nehemiah, myself. I think that's it. So and I'm number 13. So cool. That's awesome. I think I've got everyone. Yeah, so next couple days here, we're gonna get into a little bit of weld demos, stuff like that. I've got it all planned out for you guys. It should be pretty cool. Then we're gonna basically, in a week or so, jump on to shielded metal arc welding. And when we get you guys back here in the class, we're gonna jump in the booth, get some welding done there, and make the best of the time we got together. It's unfortunate that we've had to go into this COVID situation with the online learning, but I do see a light at the end of the tunnel, hopefully, and I'm going to try and make the best of the time that we have when you guys get back in the class. So I'm going to open up that quiz for you in just a moment. And yeah, you guys are free for the day here. So if you have any questions, hit me with them now or shoot me in an email. I'll answer that right away, and I'll get that test opened up, and you guys will be good. So that is that. Thank you much again for joining. I appreciate it. And you guys are free to do whatever you like for the rest of your day once you finish my quiz.
Well,
Thank you.
the quiz is gonna be in the semi-auto welding, right?
That is correct, yes.
Ah, all right, thank you.
Yeah, under there, resources and content, then we'll move over to the online tab, online learning tab or online lessons tab. Click that and you'll see December 1st one, then December 2nd one, and that is that. So there'll be a quiz right there with it too. Awesome. All right, you guys have yourself a great day. I'm gonna get that opened up for you right away here. Okay, thanks. See you guys. Have a good night.
Bye.
Bye.